I am Francis Andiskaya from BS ECE 3B, and this is my performance task number 9 for ECE 23. So today I will be discussing and showing how to solve using arithmetic coding. Arithmetic coding is a popular compression algorithm. After Huffman coding, it is particularly useful for a relatively small and skewed alphabet. Arithmetic coding is a form of entropy encoding used in lossless data compression and is normally a string of characters represented using a fixed number of bits per character, as in the ASCII code. So the objective for this task is to demonstrate how arithmetic encoding and decoding works. So for our example, I will be using my ID number 2019-2467A. So first, we need to get the probabilities of all the characters in this. So A has a probability of 0.1 since it only appears once, as is the case with the dash, 7, 6, 4, 9, 1, and 0. 2 has a probability of 0.2 since it appears twice, so therefore 2 over 10 is 0.2. So here we will arrange it from 2, which is the most probable, and the rest, which will only appear once. So in order for arithmetic encoding to work, first we will need to expand the range of 2, which is from 0.0 to 0.2. So here we have expanded it. The lower boundary is 0.2 and the upper boundary is 0.2. We need to get the middle of these two, which is 0.02. So to get this, we need to subtract the lower boundary from the upper boundary and divide it by 10. So 0.2 minus 0.0 divided by 10 is 0.02. So 0.02 will be the interval for between 0.0 and 0.2. So 0.0 to 0.02 to 0.04 and so on and so forth. And then in order to get the next number, we will be using its position here. So its range is from 0.04 to 0.06. This is based on its position here in the original graph. So just as with the previous one, 0.06 minus 0.04 divided by 10 will be the interval, which is 2 times 10 raised to negative 3. So 0.04 plus 2 times 10 raised to negative 3 is 0.042. And then you continue with it, so on and so forth, until you get to 0.06, or the number before it, which is 0.058. For 1, as is, from its positioning here, you base it, and then upper boundary minus lower boundary divided by 10, and then interval, so on and so forth, until you get to the dash. And then we have our continuation here for 2, 4, 6, and 7. As is, since 2 is repeated again, we will be using its position from the previous example. So from there, the lower boundary is 0.04696 and the upper is 0.046964. So upper boundary minus lower boundary divided by 10 is 4 times 10 raised to negative 7. So this will be the interval for this. And then 4 will be also expanded from its position here. And as is, interval again until you finish. And so we have our last character, which is letter A. So based on the expansion before it, its lower boundary is 0.046222716 and the upper boundary is 0.046962272. So this is what we will use to get our binary code. So here for the solution, we have the upper bound, which is 0.046962272, and then the lower bound, which is the 0.0469622716, and then we will get the middle bound by adding these two, and then we will divide it by 2 to get 0.0465944716. And then we will translate this into binary code, which will become 0.000101111101101, which is equal to 2019-2467A. So in order to get to basically reverse what we have done here, so in order to decode our binary and return it to a decimal form, we'll basically just use this formula to get its binary. So not counting the 0 before the period, there are 19 different numbers here. So this is the binary version. In order to get the decimal, you need to multiply this number by its position, since this first 0 is here, this counts as 0, and then the one after the period will be multiplied by 2 raised to negative 1, and then also the next 0 will be multiplied by 2 raised to negative 2, and so on and so forth until the very last one, which will be multiplied by 2 raised to negative 19. So after you multiply and add all of these, you will get this 0.46594619. So this will be how it will be decoded back into decimal form. So this concludes my report for this task. Thank you for listening.